Um, let me go over the rules one more time. If the bases are alike in your multiplying, keep the base, add the exponents. If the bases are alike in your dividing, keep the base, subtract the exponents. If you have a power on the inside and a power on the outside, multiply. If there's two things, that power will distribute in. Anything to the zero power is 1. A negative exponent's job is to flip whatever it's touching. It is super important that we know these rules. We're going to have to use them in multiple different ways, so don't forget these rules. Now, we've already done these ones, so now let's jump down to some of the equations that we see. Okay, so let's jump now to problem 25. So we need to talk about solving equations that have powers other than squares. Now, I think you're pretty good about solving quadratics at this point. You've done it probably many times. We'll review that at a later date, but let's talk about if you see a power like 25 that has a cube on it. Now, you still treat that like a standard equation. So add your 110 to both sides. Now, you don't have to show that step, but I'm kind of going to show you some steps here. And then we're going to divide both sides by 2. Now, once you have isolated that cube, the opposite of that is a 1/3 power or a cube root. Now, on a cube root is this little number inside of the radical that is called an index. So a power rule you might want to remember, I'm going to call the index n. And so the rule of thumb is the following. That is equivalent to a fractional exponent m on the top and n on the bottom. So what technically this does is it takes a 1/3 power on both sides. Now, if on a calculator, let's say you're using a calculator on your iPad, some of those calculators are a little funky. If you don't find a cube root, you can take the thing to the 1/3 power. So sometimes that is helpful if you're using a calculator, say on your phone or on an iPad. That cube root button isn't an option. On my red calculators in the back, above the caret, there is a little button that does have that cube root as an option. But if we take the cube root of 125, 125 is 5 times 5 times 5. So it's 5 cubed. So it's a perfect replacement. So we would get that x is the cubed root of 5 cubed. So that would be 5. So a cube and a cube root cancel each other out, just like a square and a square root cancel each other out. Unlike a cube root, or unlike a square root, we need a plus or minus to account for the fact that when we square something, it could have been a positive that did it, it could have been a negative that did it. An odd power gives you what it gives you. So the answer is positive 5. We don't have to worry about anything like a plus or minus like we would in a square or a square root or a 4th root or a 6th root. Yes. Oh, so if it doesn't work, like if it's not perfect like that, like if you see this and you get like the cubed root of 6.5 is nothing great, you're just going to have to use a calculator. For iMath, you probably can just put that in. If you use that little yellow box where that equation editor comes in, you can put probably their cube root's probably an option. So I would practice, or just now at this time, if you want to look at your particular calculator that you tend to go to, make sure that you get this decimal for the cube root of 6.5. That's a little one to kind of check your work. Again, you can make this 6.5 to the 1/3 power. So if you have a power button, that is an option. Square root is a 1/2 power. Cube root is a 1/3 power. 4th root is a 1/4 power. So you can use that as an option as well. So just make sure you have found a calculator that you're comfortable with using that particular those roots or things, okay? Because yes, sometimes it doesn't come out real perfect. Everyone good with 25? Okay. Now if we could please jump to problem 28. Now for problem 28, it's the same sort of technique as before. We're going to isolate that variable just like always. Now I would suggest that we can immediately deal with the 1/2. Why not multiply by that common denominator? So then we don't have a fraction to worry about. 1/2 and 2 multiplies together to give us 1. I suggest if you have fractions, multiply through by the common denominator. It's always going to make that equation look a little nicer to begin with. And we're left with x squared plus 5 is equal to 164. Now we're going to subtract 5 from both sides. We get that x squared is 159. And again, just like if we have a cube, we want to use a cube root. If we have a squared, we want to use a square root. But the difference is that we do have to put a plus or minus notation in front if our index is even. Now, technically, we don't show it, but there is a little 2 right there. It's an index of 2 on a square root that matches that square that we started with, that 2 power we started with. So anytime it's even, you have to remember that there are 2 possible solutions. In this case, plus or minus 159. Now, 159 is divisible by 3. But it's 3 times 53. Neither of those numbers are perfect squares that we can make pretty, so just leave it. I'm okay with just leaving it and putting, using that little equation editor in the yellow box in iMath. You have to include that plus or minus symbol or they're going to say it's wrong, okay? If they say to separate the things by, you'll have to explore if they want a positive square root of 159, comma, a negative square root of 159. I don't know, so we'll mess with that when the time comes. Okay. And then let's look at this one. Now, it's a whole different ball game when our variable is up in the power location. Now, until we go through this particular lesson, I can't give you too many tools right now, but I will give you some more tools to solve that more effectively. But let's talk about what we can do. Since 54 is divisible by 3, I would suggest, because distributing isn't going to do much, we can't really multiply 3 and 3 times 2 to the x is just that. It doesn't do anything. So let's divide the entire both sides by 3. We're allowed to do that. Just like we're allowed to multiply both sides by anything, you're allowed to get rid of that 3. 54 divided by 3 is 18. So this would just be 2 to the x minus 14 equals 18. And isolate that term that has your x on it by adding 14 to both sides. And we get that 2 to a power of x is 32. Now, here's where some logic comes into play. We're really looking for what power do we put on a 2 to get a 32. Now, for now, it's going to be ones that should work out nicely. Otherwise, we will use a calculator, and I'll show you eventually how to do that. But we know that this is really, 32 is really 2 times 2 times 2 times 2 times 2, or 2 to the 5th. So our answer then is staring us in our faces here. X would have to be 5 to make this work. So what we can do is we can put a 5, right in this spot right here. If we put into our calculator 3 times the quantity of 2 to the 5th minus 14, we should get 54. So you can check these nicely with a calculator. Solving them with a calculator, I'll show you eventually how to work that. We're going to use some fractional exponents to help get us there. But sometimes it's a matter of kind of a logical sort of thing. Now, we may revisit this paper at another time, but for now, in Google Classroom, please turn in mod 4.0, and while you're in there, please get mod 4.2. Okay, so please turn in mod 4.0 while you're in there, and then we're going to start mod 4.2. Now, mod 4.2 is going to start exploring that exponential behavior. So most algebra teachers do exponential functions and logs usually near the beginning, or I'm sorry, near the ending of the year. So hopefully, most likely you have worked with these before. For linear functions, there was a constant rate of change. That slope was a constant. What happens in an exponential function is the pattern, the input and output vary. There's a covariance. So it's going to be a little different when we explore exponentials in this section. Exponential functions have a look to them. So instead of linear, that's like an exponential growth. You lived through it. Our pandemic followed an exponential growth pattern, the number of cases. And then eventually we got vaccines and more people were exposed, and then it became an exponential decay pattern, so which was awesome for all of us. But anyway, so exponential patterns do actually occur in real life. It's a common thing, not perfectly, but they do occur many times. Okay, so let's look at exercises 1 through 5. Okay, it says when a piece of new technology is invented and sold, its value decreases over time because it wears down and becomes newer. Better technology is developed to replace it, and so on. Suppose two electronic devices have the same resale value right now, and that their resale values are expected to change according to the following patterns. So let's look at the patterns that they're talking about. So I'm just looking at this little thing right here. Okay, so product 1 says that the current resale value is 300. They're both a resale value of 300. The resale value is expected to decrease 30% per year for the next several years. And then the product number 2 says the resale value is expected to decrease $45 per year for the next several years. So in A, it says, find the expected resale value in dollars for both devices 1 year from now, and then we'll demonstrate how we did it, obviously. Okay, so let's look at product number 1. So for product 1, let's think about what it said. It's expected to decrease by 30% per year. So it's going to go down by 30%. So if we multiply by 70%, remember that 100 minus 30, we explored a little bit in 4.1. If we multiply 300 times 70%, so let's change it to its decimal equivalent, we get that its value will now be $210. So hopefully that makes sense based upon the stuff we were talking about before. Now, product number 2, it just goes down exactly by a value of $45 per year. So if we take 300 minus 45, it is now worth $255. So that would be the value of each of those particular items. Okay, everybody see how we got those initial values. Okay, so now we've done that. It says, without performing additional calculations, Predict what each device will have, or which device, I'm sorry, will have a greater resale value 6 years from now. Well, what do you guys think? Based upon what we got so far, which one is going to have a better value after 6 years? Anybody have an idea which one they think is going to be worth more in 6 years? The second one, okay. So product number 2. I agree, even just looking at what we see there, it's looking as if product number 2 is going to win the race, okay? So now that we've kind of thought that through a little bit and thought, well, it looks like product number 2 might be. Let's go ahead and let's fill in the chart. Now, what I want to do first is I want to fill in the inside of the chart before we go to the outside, okay? So let's fill in this part. Now, the first one, let's assume that this one, because that's called that iTech, see it says iTech right there. This is product number 1, and this is product number 2's, okay? Okay, so let's fill out what we know about product number 1. It's going to go down by 30%, or each year we get to multiply by 0.70. Okay, so we found this was 210. And if you have a calculator, if you did 210 times 0.70, then it's 147. And if we keep doing this, is 102.90. And then it's 72.03. And this is 50.42, rounded to the nearest penny. And then I'm keeping multiplying by 0.70 every time. That's 35.29. Okay. So in the 6th year, our product number 1 is worth $35.29 based upon what we see there. Now, we're not going to do the delta T over delta S just at the moment, okay? Okay, now let's jump over to the one where it says just every year it's going down by 45. We already did this math. This was 255. Now, if we take off 45 again, that's 210. If we take off 45 again, that's 165. And then I'm going to just keep on taking 45 off. And this is 75. And this is 30. So let's look at what happened. So we were kind of instinctually, we were kind of right, kind of. Look at every single year. Year 1, product number 2 was ahead. Year 2, year 3, year 4, year 5. What was the first year where that changed? Year 6. So when I looked at it, I agreed with you. I thought product number 2 was going to win. But if we look at the chart here, there was a time where they crossed over. Now, if we have an equation for these items, this equation to the right was higher because remember our Y value would be more than or higher until year 6. And then year 6, it ends up being lower for the first time. So if we look at the graphs, this graph to the right, let me show you, is a linear graph. The graph to the left is an exponential graph. So let me show you why. Here, we went up by 1. Here, we went down by 45. Up by 1, 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 down by 45. It is a constant rate of change. The slope, delta N over delta T, always negative 45. If we had an equation for this one, it would be that the amount of dollars is 300 minus 45t. That's an example of a linear equation. Okay. Now let's look at product number 1 for a moment. And I want to show you what's happening. It's a little different. It's weirder, okay? Yes, we went up by 1, up by 1, up by 1. That's not changing. But our delta S is not going to have that exact perfect constant rate of change. So let me show you what happened. Here it went down by 90. Here it went down by 63. Here it went down by 44.1. Here it went down by 30.87. So we explored, here it went down by 21.61, that a discount like this or a decrease in value like this, the calculation depends upon the original value. So the original value kept changing. So at first, the original value was 30. When I took 70% of that, I got 210. And then the next one, I got 147. So the value we're reflecting back to kept changing. And so that's why we kept getting these different values every time. But what pattern do you notice about the amount that's coming off the change in price each time? What do you notice about those price values? Each time they're going down. So, and that's because we're taking 70% of something that is smaller than the one we took before. So there is a pattern. It's not constant. It is decreasing. So this would look something, it would be a decreasing kind of curve to it. And that's what we should expect as something decreases over time. And so what happened was this function might have been going like that, and then this function was higher until a certain time. So, check your conviction. Okay, so we were wrong. It's product 1. The table on the left demonstrates how the expected resale value co-varies with elapsed time. What stays the same as these two quantities' values change? That would be that 0.70. That 0.70 was used every time. On the table of right demonstrates how the expected resale value co-varies with elapsed time. What stays the same as these two quantities' values change together? And that would just be their delta, what did they call it? Delta N over delta T was constant. And that happens for a linear equation. In E, we have that change, but it is decreasing, which is important, okay? So now we're gonna, let's do just the first one, okay? I did come up with a formula. Did I come up with a formula for the, no, I came up with the easy one first. Let's do the Dynasystems device. It started out at 300. It minused off 45 for every year. So that one was a pretty nice one. We have seen equations like that. But let's talk about the equation that's happening for the second one, or the first one, the iTech. For that one, every year we have to multiply by 0.70. So we started out with 300. That is our starting value. That 300 has to appear. But what's interesting, we have to take 0.70 and multiply it. If it was 1 year, we have to multiply it once. If it was 2 years, we multiplied it by it twice. And so it becomes something like that. So the difference in these two equations, here our variable is to the first power. It is a linear equation. This one, our variable is up as a power, when that's happening, that is an exponential equation. So we have these equations. So let's go ahead and let's evaluate some things, okay? So remember, I'm going to write these down here so we have them. So f of t is 300 times 0.7 t. G of t equals 300 minus 45t. This f was s. I don't know why they called it s. And this quantity, their y value, they called n. I don't know if we need that, but that'll be helpful, okay? So there we have those equations written down. Then we can use them, then we can use those values, okay? So f of 4 means after 4 years, what would be the price for product number 1? So f of 4 is going to be, product 2 was the exponential. So that's f of 4 is 300 times 0.7 to the 4th. And you can call it 0.7, 0.70, 0.7, any of those things. Okay, and we get 7203. Now, if we go back to our chart for a moment, that better be the 4th year. Look, year 4, 7203. So our formula is correct. That's why we can kind of check our work. The other one that uses F, let's go to this one. Now this one says, what is the year where we get an answer of 147? So if we have a chart, which we do, we need to find out the year where we get 147. So it is on the chart, that value. So our time is 2 years. So remember that inverse notation, that's the inverse of f. So the inside there is the value is 147. What time did that occur? Okay. Now let's use our g function. G of 3 is 300 minus 45 times 3, which is 165. So if we go back, I always like to look in my chart. So we got an answer of 165 at year 3. Did we get a value of 165 at year 3? So this is a way to kind of check our formula. This is more the logical way of done. Did our formula get us the same thing? It did, yay. So we're on the right track. Now here, this is the linear function at 6 minus the linear function at 2. Now we have the chart values. At 6 we were worth $30. At 2 we were $210. So we could just do 30 minus 210. That is the change in the value from year 2 to year 6. Remember, it's always end minus beginning, and that's why it is worth negative $180. But we also could have plugged 6 into our function, we should get 30. Plug 210 or 2 into our function, we should get 210. Okay. I'm just trying to think here. So now I would like to jump, please, to the graphs, because I want to explore what the graphs are going to look like. And if I have time, you know how, if we have time, we'll explore exponential functions more, what they look like. But you're going to see that curvature, and it's going to skim towards 0. These graphs always have what is called a horizontal asymptote. It's never going to be completely 0, but it's going to get super close and super close and super close and super close, okay? Here is our linear function. We started at 300. If you explored that slope, that negative 45, we went down 45 and over 1, and down 45 and over 1, and down 45 and over 1. This doesn't have that. It has that curvature to it, okay? And so look what they've done here. They've just pulled out the exact values and see how these are perfect and these are not, okay? Now, obviously, we can have a 2.5 years, so that is a continuous function. We would connect those dots. Okay. Let's see if there's anything here for 5. No, we're good. Okay. So just let's talk about this a little bit. So if you want to highlight some stuff. Exponential functions have a constant percent change, okay? That might be a growth, so it might be a number more than 1. It might be a number, a decay, or a decrease or a discount. It might be something like we saw in the value of the phone, where that 0.70 was less than 1. But it is always going to be some quantity value that we're going to have to use a power on. An exponential function, the variable is our exponent, and so that's kind of what they're getting at, okay? So you have the rest of the period. You have 2 homeworks that are due on Sunday. You have 4.1 and 4.2 homework, I believe. Turn these 4 2 notes in right now. We'll explore exponential behavior a little bit more as the week goes next week. Grades are coming due. The deadline for grades is October 13th. If you do a late pass and it extends past October 13th, I don't care. Whatever's in there October 13th, that's the grade you're getting, okay? So feel free. There's going to be a ton of homework due on October 13th, so just prepare yourself. October 13th is the deadline for my grades, okay? So there you go. Do some iMath, please.